All right, let's dive in. Today, we're basically becoming code breakers. We're going to crack the algebraic code by really getting a handle on two of its most important pieces, exponents and polynomials. So let's get started. You know, if you've ever just stared at a page full of X's and Y's and felt like you were trying to read some kind of alien language, you're definitely not alone. But here's the thing, it is a language. And just like any language, it has rules, it has patterns, and this right here, this is going to be your decoder ring. So, every code has its keys, right? Well, in algebra, one of the most powerful keys you can have is the exponent. Seriously, once you master this one little symbol, you'll see how everything else just starts to click into place. So, what even is an exponent? Well, it's really just a simple shorthand for multiplying a number by itself over and over again. I mean, instead of writing out 2 times itself 5 times, we can just write 2 to the power of 5. That big number, the 2, that's our base. And the little number up top, the 5, that's the exponent. And it's just telling us how many times to multiply that base by itself. Now this is where things get really useful. These 3 simple rules let you handle some really complex-looking problems. When you multiply terms that have the same base, you just add the exponents. When you divide, you just subtract them. And when you raise a power to another power, you multiply. You get these 3 down, and you've basically mastered the core of how algebra works. This right here, this is the main takeaway. Don't just try to memorize a bunch of formulas. Understand the pattern. Multiplication goes with adding exponents, and division goes with subtracting them. It really is that simple, and it's a huge shortcut. Okay, there are also 2 special cases you're going to see all the time. First, anything, and I mean anything, to the power of 0 is always 1. Doesn't matter if it's 5 or 5 million, it's 1. And second, a negative exponent does not mean the number is negative. It just means you flip it. You take the reciprocal. So x to the power of -3 becomes 1 over x to the power of +3. Getting these 2 down will save you from so many common mistakes. Okay, so we've got our keys. Now let's see how these keys build something bigger. If exponents are kind of like the individual letters in our code, then polynomials are the phrases and the sentences they create. This is where we start putting our symbols together into expressions that actually mean something. So a polynomial is really just a string of terms that are being added or subtracted. Each little piece, like that 3x squared, has a coefficient, that's the number out front, a variable, and of course, an exponent. And that number at the very end without a variable, like the -7, we just call that the constant. That's it. They're just expressions built from these simple little parts. Now, we can sort polynomials by their degree, which is really just a fancy way of saying the highest exponent you can find. A degree of 1 is called linear, a degree of 2 is quadratic, and a degree of 3 is cubic. You can almost think of them as different kinds of sentences. They all create unique shapes and tell different stories when you put them on a graph. Okay, this is a really important grammar rule for our algebraic language. For an expression to be a true polynomial, it has to play by a few rules. The exponents have to be nice, whole numbers, so no fractions or negatives. And you can't have any division by a variable. So if you ever see a variable hanging out in the denominator, that's a red flag. It's not a polynomial. So now that we know what these algebraic phrases are, let's learn how to combine them. We're going to start with the basics, adding and subtracting. This right here. This is the single most important rule in this whole section. You can only add or subtract like terms. What does that mean? It means they have to have the exact same variable raised to the exact same power. You can add an x squared to another x squared, no problem. But you can't add an x squared to an x cubed. They're not the same thing. Adding is pretty straightforward, actually. You just drop the parentheses, then you gather up all your like terms, put all the x squareds together, all the x's together, all the plain numbers together, and then you just combine their coefficients. It's just like sorting and counting different kinds of algebraic blocks. Now, subtraction is almost identical, but it has one critical first step that trips up so many people. You have to distribute that negative sign to every single term in the polynomial that you are subtracting. It flips the sign of everything inside those second parentheses. As soon as you do that, it just becomes an addition problem. Let's just lock this in because this is probably the #1 place where mistakes happen. Always distribute that negative sign first. Make it a reflex. I promise it'll save you a ton of points on your next test. All right, so we've combined phrases. Now, let's see how we can build even more complex sentences using multiplication and division. So when you're multiplying two binomials, which are just polynomials with two terms, there's this great little acronym that helps you remember all the steps. FOIL. You multiply the first terms, then the outer terms, then the inner terms, and finally the last terms. After that, you just combine any like terms you have, and you're all done. Now, for anyone who's getting ready for a big standardized test, this slide is pure gold. Seriously, test makers are obsessed with these patterns. If you can spot a difference of squares or a perfect square, you can just jump straight to the answer without having to do all the FOIL steps. Think of them as algebraic cheat codes. Division can get a little tricky, but the most common type you'll run into is dividing by a monomial. That's just a single term. And the method is actually pretty simple. You just split the problem up into smaller pieces and divide each term in the polynomial by that monomial one at a time, using that quotient rule for exponents we talked about earlier. So we've learned the keys and the grammar of this algebraic code. But let's take a step back and ask, why does any of this matter? Let's take a look at how this code actually describes the world all around us. You know, this isn't just stuff for a math test. In physics, that little squared term is absolutely essential for describing how gravity affects a thrown ball. In the business world, these kinds of functions are used to figure out the maximum possible profit. Engineers use them constantly to design everything from bridges to computer chips. It really is the language of science and business. And hey, let's be practical. For a lot of you, the most immediate reason this matters is to do really well in school and on those big tests like the ACT. Getting good at these operations is a direct path to bumping up your score because these types of questions show up over and over again. So, you see, algebra isn't some arbitrary, secret code meant to be confusing. It's a really powerful language for describing patterns and solving problems. And now you have the keys and you know the rules. So the only question left is, what problems are you going to solve?